Next presentation is about process intensification, or what I call computer-aided process intensification. So, as I mentioned in the previous lecture, our overall goal is to attain sustainable circular economy. So note that I'm talking about not circular economy, but sustainable circular economy, which can be slightly different from what Professor Pistikopoulos will talk about also. In my view, because of our laws of thermodynamics, circular economy cannot be achieved exactly. Over time, the circle has to go to a center because of entropy. So the idea of sustainable is how long can we sustain this economy before we replace it with another. So that's the idea of the sustainable circular economy. So based on this, we define the process intensification objectives. And then what we can see is that there are many ways to achieve process intensification. Almost everybody can claim that they are doing intensification. So there are many ways to do it, and we have to be clear what are those ways. And what I've listed in the third column are some of the ways to achieve process intensification. It is not by no means a complete list. So we can achieve intensification through higher productivity, better species utilization, supply chain, through multitasking, equipment operation, increased efficiency, safe and reliable operation, economic improvement. So these are some of the means to achieve the objectives. And then how do we achieve these objectives? So then the means to achieve these objectives, sorry, the previous one, these are the sub-objectives of process intensification, that if we want to achieve sustainable circular economy, we can achieve PI objectives of higher productivity or multitasking and so on. But to achieve these, there are different means. We can look at a better reaction path. We can look at better species allocation, heat and power management, rate size mechanisms. That means the transfer rate is connected to what is the size of the mechanism, tasks and equipment, scale up, scale down, controllability, operability, and many more. So all of those things can help us to achieve some of the objectives that I've listed. And then the means to achieve these objectives I've given. What is the result of that? By one or more of those means, if we achieve the objectives, we will see that we have defined a novel network, a new network of processes that can be called a module, that can be called a flow sheet, and that can be called enterprise in a larger scale. We can have novel integration schemes. We will see that we can generate new intensified equipment. We can have new processing routes because of reaction, species separation, and so on. So all of these results can be achieved through the means to achieve the PI, and the means to achieve the PI will give us the objectives criteria that we would satisfy, which would then lead to sustainable circular economy. So let us see some examples of intensification. On the left, you see the actual process that we have also used during the first and second webinars, is for production of methyl acetate from reaction of methanol and acetic acid. The entire process can be now represented by reactive distillation, which will give exactly the same product. So that's process intensification. And in a similar way, this is also a process that actually has been designed and converted. So in the case of edible oil. The final step of edible oil is to remove some chemicals that have not good smell, so you don't get bad smell in your food product when you cook food. But these chemicals that have bad smell and that has to be removed are actually quite expensive products that are needed by the pharmaceutical industry and the food and some other industry. So it is valuable to separate them and use them in other industry. The process you see on the left can be converted into one equipment where there are multiple subsections doing all the operations that you see on the left. So the question then is, can we have a computer-aided system that can take this process on the left and give us the result on the right? And we will see how to get that. And then other examples of intensified equipment, like a dividing wall column, distillation, mixing operation, reacting mixing operation, a separation operation, and another example of not converting everything into one equipment, but just reducing the size, reducing the number of unit operations. So these are all engineering domains that we know commonly very well, but there are other domains that also are intensified operation. For example, the space module that goes on the space missions. If you take all the heat exchangers and all the other equipment that are there and put them out flat on some land, you will see that it will cover more than a football stadium. So there's a lot of integration and intensification going on a space module. Also for power plants, gas turbine, combined cycle gas turbine, there's a lot of intensification. Even in food production, if you are familiar with Krispy Kreme donuts, these people have actually, through intensification, reduced the number of production steps from more than 10 to only 6. That's a good example of intensification also. So there are lots of examples of intensification. Even in products, what you can see is that these are chemicals, not the red and black are polymers actually, and the other one are larger molecules. And the really long molecule is a lipid, surfactant. They have multiple purposes. For example, the surfactant on one end, it is hydrophobic, and another end, it is hydrophilic. So if we can define molecules having different functions at different ends of the molecule and also the polymer, that also is doing the same thing as a intensified operation. Similarly, this kind of emulsions, water-based or oil-based, and also formulated products, they all have multiple functions. So even the product can be called an intensified product. So now we define the computer-aided process intensification. It refers to the use of systematic model-based technique to realize potent process intensification, that is to determine and analyze process intensification solutions. So process CAPI techniques for process synthesis design analysis help to tackle challenges and accept opportunities by working at a single or multiple scale. And the scales can be unit operation, task, and or phenomena. So unit operation is large, task is smaller, phenomena is smaller. And if we want to go in the other direction, unit operation will give module, module will give network. So we can do in both directions. Satisfying also a set of process and operational specifications, as well as match a set of improvement targets. That's what computer-aided process intensification technique should be able to do. So let's look at the issues and challenges and concepts. The first question is when to apply process intensification. And two examples are given. We have a process design to make a product from raw materials A and B. We would like to determine process intensification alternatives that are better than the reference with respect to a set of design targets. Another one could be information of product C and raw materials A and B are given. Determine the optimal intensified process with respect to a set of desired targets. So the first one requires that we have a reference, and compared to the reference, we will find better alternatives. The second one does not require a reference. From the beginning, our objective is to find the optimal, which can be more difficult. So the main issues then, how to represent the PI alternative. Which scale should we use to represent? Because if we are not working with unit operations, we do not have a flow sheet like the unit operations. So we need to find the scale and the representation system. How to generate innovative process intensified alternatives. So just like we saw in the case of process groups, what way should we combine different unit operations to perform in a multi-operation way? So we need some combination rules. How to evaluate alternatives? We need models, and if the scale we used are not unit operations, do we have the models to do the simulation? How to identify the best optimal solution? We need to find an appropriate solution strategy and also performance criteria by which we will compare. What information data needs to be supplied? It needs a lot of data. How can we get that data? And the solution approach, this is just one way. Professor Pistakopoulos will give you another way. Solve the following steps sequentially or simultaneously. Generate alternatives. Check for feasibility, that all those alternatives that you generate are feasible. Evaluate the desired targets. That means after feasibility check, calculate the performance criteria, which defines the targets, identify the best or optimal. And what we can do is, if we use things like maximum driving force and things like that, without doing the optimization, we can be very close to the optimal solution. So representation of the PI scheme in different ways. This is the phenomena based, and then the phenomena combined together gives the unit operation. This idea was developed a long time ago by Professor Pistakopoulos and his co-workers, and it forms the basis for all other methods, because we have to go to the phenomena and identify how the phenomena will be used to perform the task that we need, and how the task can be combined to become the unit operation. But he will talk more about it, so I will not go into details of it. But what I will do is how we have developed our phenomena-based method using the same concept. So let's say that we have a separation problem, and we have a three-component A, B, C that we want to separate. That is at the top left. And then we have looked at, we have a library of phenomena that we have found are mostly used in chemical processes, biochemical processes. There are about 16 of these phenomena. And this phenomena is mixing, phase contact, phase separation, phase transfer, heating, cooling, drying, reaction, and so on. So using those phenomena, we combine them in certain manner, and we call them simultaneous phenomena building blocks. What is a simultaneous phenomena building block? What you can see, if we take the top one, it says that in this building block, there is mixing, there is cooling, there is two-phase mixing, there is phase contact between vapor and liquid, phase transfer between vapor and liquid, phase separation between vapor and liquid. So essentially, it's some kind of a flash. And similarly, we have another one in the middle that does not have heating or cooling, and the one below is heating. So like this, we can actually prepare a library of simultaneous phenomena building blocks. And then once we have this library, we have a library of blocks like that. And it's not that we will have thousands of them. It's actually less than 1,000. Then we will take these and we will combine them together into a basic structure. And what we say is that this basic structure, which will perform a task that has only one SPB with a cooling, has a SPB without cooling or heating in the middle, and has a SPB with heating. That's one unit. Okay, and that is what we call a basic unit. And then what we do is we check by solving this. We have the models for it to do mass balance. We can check if the output that we get from this, for the vapor output at the top and the liquid output at the bottom, do they satisfy our product specification, process specification? If not, then we have to do something. So what we do something is what we call intermediate SPBs, and these intermediate SPBs can be repeated as many times. So what it means is the top one with the cooling is fixed, with the heating is fixed, but the middle one, that can be repeated as many times as we want. And then you can see here, we repeat it a number of times. And then if we look at, it actually represents a distillation column. The number of stages below the condenser and the number of stages above the reboiler. So that's a distillation column. And in the same way, if we do two of them, it will be a dividing wall column. Okay, so from the concept of phenomena, SPBs, basic structure, and repetition of the intermediate SPB, we can configure almost any unit operations involving, let's say, vapor liquid. And of course, other phenomena is also possible. So that's basically the method. And there is also another person at Texas A&M, Farooq Hassan, who is also working on intensification using the phenomena-based approach. And he defines a building block and represents everything with building blocks, and then he performs an optimization to get to the final solution. We will not discuss this in detail now because it will take a lot of time. So then let us see that why the phenomena building blocks can give us better solution that we cannot otherwise get. And this comes back to the molecules and mixtures. So let us say that we have 4 molecules and we want to find out from them if there is a mixture, binary mixture that is the best. So if we have 4 molecules, the number of binary mixtures we can make is 6. So we can easily calculate 6 binary mixtures and see which one satisfies our requirement. So there's not many alternatives. But if we say that we do not have 6 molecules, but we have molecular groups like CH3, CH2OH, and how many compounds can we make with minimum 2 of these groups and maximum 4 of these groups? We will see that we have more than 6 molecules. And if we have more than 6 molecules, we will have more than 50, at least more than 10 binary mixtures. So we can see that by going lower in scale, we can have more alternatives. And if we go even lower in scale to carbon, hydrogen, oxygen, how many ways can we make groups with carbon, hydrogen, oxygen? And then once we have made these, how many molecules can we make? And then how many binary mixtures can we make? It will be millions. So the lower in scale we go, we have more chance of finding a solution that otherwise cannot be found. And can we use the same idea in flowsheet process intensification? So we have the unit operations. We break down the unit operations into individual ones, and then we can say how many ways can we combine them with 3 unit operations. And if we want to use all of them in a certain way, we will not have more than 3 to 6 alternatives. If we then break down the unit operations to tasks, what does a mixing task include? What does a reaction task include? What does the separation task include? And how many ways can we do the mixing, separation, reaction? And because we will have more than the 3 that you see in the unit operation level, so we can get more flow sheets. And then we can reduce the tasks to phenomena. What are the phenomena occurring in mixing, reaction, two-phase mixing, phase contact, phase transition, and so on. And then these will, when combined, will give us more tasks, which when combined will give us more unit operations, which when combined will give us newer flow sheets that the unit operations otherwise cannot find. So that's the great idea of going lower in scale and then recombining them to get to the unit operation scale that we know. So now we can see that our defined objectives, PI objectives, we know what we need to do, and then we have the means to achieve those objectives. On the right, some examples of the solution of the PI objectives and how can we do it, the method. We need multi-scale process intensification method. We can do it in phenomena level, we can do it at task level, we can do it at operation level, we can do it at network level. And this we have talked about before, so I will not explain too much, except that whatever alternatives we are generating has to be inside the reference. So the solution approaches and tools. I've discussed this also before. We represent this mathematically, and in mathematically we have the objective function, we have the process constraints, and so on. Depending on the model, it will be solved as linear programming, nonlinear programming, mixed integer, process simulation, and so on. And the solution strategies, there are direct solution strategies, decomposition based. Others are doing direct solution approaches. We are doing the decomposition based approaches. Both have advantages and disadvantages. I like better the decomposition based because it gives us more flexibility and we can solve bigger size problems and more complex problems. So how does the method work? I will give you, it's a very busy slide, but you will see that by following the directions, you can see how the methods work. There are 3 methods that I'm highlighting: the rule-based method, the direct solution method, and the hybrid solution method. So the rule-based method needs a reference flow sheet, and we go back to the methyl acetate production. So we have this flow sheet. We analyze the flow sheet. That's the means and end analysis. Find out where the problem is and try to resolve the problem. So the next step, at every step, we identify one problem, we resolve the problem, and the flow sheet becomes smaller. So which problem did we remove from here? Analysis of the system shows that there are 3 isotopes and 2 of them are with water. So if we can remove the water as soon as possible after the reactor, then we have less problems in terms of separation. So that's why the first thing we do is to get rid of the water. Then we see that can we actually combine the water separation in the reactor, so we don't need the water and the reactor separating, doing the operation separately. So we combine the water separation and put that into the reactor. So then we also reduce that separation step. And then we find out that methanol and methyl acetate forms an isotope. And by changing the pressure, because it's pressure sensitive, with 2 distillation columns, not requiring any solvent, we can get the pure methyl acetate and we can recycle the methanol. However, if we want to put them all in the distillation column, how can we do that? We can find out how much methanol is needed to be on the side of the isotope, which will give us pure acetic acid, pure methyl acetate. Because in the case of isotope, if you are on one side, you will get pure methyl acetate. If you are on another side, you will get pure methanol. So we adjust the methanol so that we are on the side that gives us the pure methyl acetate. And then internally, the methanol methyl acid isotope will be flowing downwards in the column. So we get rid of then the 2 columns into 1 column, and then the acetic acid part that you see after the reactor and the water separation, we put it below the separation of the water. And then we have the reactive distillation that you see on the right. Okay, so by means-ends analysis, that's how we will get it. But you can see that a lot of analysis is needed, a lot of data is needed, which ProCAFD can generate. The next is the direct solution approach. Here, whether we use the Pistikopoulos method or the Hassan method, we start not with the flow sheet, but with the idea that we have the methanol reacting with methyl acetate to give water, methanol reacting with acetic acid to give methyl acetate and water. And the reaction is not complete, so we get methanol and acetic acid also coming out. And then all the phenomena that may occur have to be collected, and then with those different combinations of blocks will need to be defined and put in a system boundary with all the blocks, and then set an optimization problem. And the optimization problem will say which are the blocks that are needed and which sequence. It can be quite difficult to formulate the problem, but the developers say that they can find these solutions. The third approach, so let me go from here to here, and they also get the reactive distillation. And the third approach, again, our hybrid approach, we start with a reference, and based on the reference, we convert the flow sheet in terms of unit operation to task. We have a table that takes the unit operation and converts them with a table that this kind of unit operation has to perform this kind of tasks. And so based on that, we can easily convert a flow sheet into a task. And then we have a table which says for each of those tasks, which are the phenomena. And then once we have the phenomena, we go to our list of library of SPBs, simultaneous phenomena blocks. And then you see 2 examples of this, a separation task, a reaction separation task combined together. And then these simultaneous phenomena building blocks put together gives us this. At the top, we have the condenser. At the bottom, we have the reboiler. And in the middle, we have reactive separation units or tasks. And then we adjust the number. We can also have reaction and without reaction. So those are the intermediate simultaneous phenomena blocks. We can have as many as we need. And by combining them, we get exactly the reactive distillation. So now you can see with computer-aided techniques, we can actually generate intensified process units. There are lots of examples of reactive distillation. That's why there is a lot of application examples of process intensification on reactive distillation. But we will talk about others also. So coming back to our original, we need the innovation and we are applying the intensification. So we want to generate new intensified options that match the design targets and make process more sustainable. We start with the reference process, we convert that into tasks, and then we look at the means to achieve the process intensification and which of the results we are interested in. And by combining the different phenomena and tasks, we can get to any of the solutions on the right. And I will, okay. So how do we do this? As we are talking about that, we do it in a decomposed way. So we need the reference process, operation, and equipment. So if we have the reference process, we know which tasks are needed, which phenomena are needed, and then we create a superstructure. And then from the superstructure, we enumerate all possible combinations. And this is the superstructure. On the left, you see the reactor. After the reactor, because 4 compounds are coming out, we need a separation for 4 compound separation, then a 3 compound separation, then 2 compound separation. And then the different alternatives you see, or different boxes you see, are the different alternatives for 4 compound separation, for 3 compound separation, for 2 compound separation. And these are generated from the phenomena going to task and going to unit operation. So in order to generate this superstructure, we go back to the phenomena and we go back to the tasks. But we generate this superstructure in terms of unit operation. And then it's just a question of making sure that we have all the possible alternatives, feasible alternatives. And then we can do the calculation and find out which is the best. There are other ways to do it. There is a paper, review paper coming out from Texas A&M, and Professor Pistikopoulos' former student, who's now a faculty member in a university in USA. This paper gives a list of many of those tools. And going back to our method, as we said, we define the target and then we identify alternatives for the target. But in order to do that, we need to have a lot of information that is generated from the process synthesis stage and the design analysis stage. So I think it will be very good to give you some illustrative examples. So here is a process that we have taken from the hydrocarbon processing annual yearbook or encyclopedia. You can, so one good source of which process to take and see whether intensified alternative can be found. One way to look at it is to go to hydrocarbon processing annual yearbook, which gives a lot of processes, and select some. Especially if there is one with 1 reactor followed by separations like this one, it is a good candidate. So we have a base case process and we could find the patent for this process design. So we have all the information. We convert in A, the process flow sheet into tasks and then in B, for each task, what are the phenomena involved. And then we combine all those phenomena involved into a list of phenomena. Then from this list of phenomena, we find out which are the simultaneous phenomena blocks that can be formed from this phenomena. And then based on that, we create the superstructure. And then after the superstructure, we just try to find out what is the best separation for 4 compound, then 3 compound, then 2 compound. And then we have the solution. And I will show you the solution afterwards. But here also you can see that alternative 1 is reactive dividing wall column, reactor followed by dividing wall column and distillation, then reactor, distillation, divided wall column, then reactive distillation, divided wall column, and the last one, everything together into one. And there can be many more. When I use this for teaching purposes, I ask the students to generate an alternative which is not in the 4 that I'm showing. And then we have the reference, and then we see that our alternatives are much better than the system that can be found in patent. So this is one example. Another example, we will take the methyl acetate example because it shows another way of doing the things. So we have the information about the reaction. We have all the information about the compounds. We have defined the objective function, which we want to minimize. The base case design is the flow sheet. And then we analyze the flow sheet in terms of sustainability, and also the indicators like the closed path and open path. And you can see an example of the closed path and an example of the open path. Open path is things come in and go out. So what we see is that the methyl acetate is going out, and the closed path has some problems, which we will see now. The problems will be looked at in terms of utility cost, energy demand. In the closed path, also the energy demand, carbon footprint, and so on. With the utility cost, we can get the pie chart, and from the pie chart, we can easily see which unit operation has the problem. And we also do the utility cost in terms of skyscraper plots and footprints. And again, we see that the bigger pie cuts also represent the largest skyscrapers. And based on that, we can say that we need to reduce the energy demand. We need to reduce the number of operations. We need to increase the conversion of acetic acid. We need to explore the possibility of using hybrid unit operations. We need to improve the sustainability and LCA factors. So these are all there. We know that we have to do something about the reactor, something about the distillation columns because the reboiler duties are high, and so on. So now we go to the process analysis. We look at the thermodynamic insights. And remember the binary ratio matrix, we have 4 compounds. So we have 6 binary pairs. We check all the binary pairs and what are the problems with those binary pairs. We look at their isotopes and we see that one of the isotope is pressure sensitive, the other 2 are not, and water is present in 2 of the isotopes. Then we find out whether we want to do reaction or separation. What are the phenomena involved for each of those isotope separations as well as all other separations. So we have a list of all the phenomena building blocks. These are the original phenomena. Remember that the PBB or phenomena building block are combined to form the simultaneous phenomena blocks, which are combined to get us a basic structure. And then we start with the original process. We know after the reactor, we need to separate. And then what are the different possibilities? And after that, what are the different possibilities? for 3 compound and then 2 compound. So knowing this information, as we said, we needed to separate water out. So the first separation we will do out of the 4 compounds is remove the water. And once we remove the water, the 3 compound separations become easier because we have an isotope between methanol and methyl acetate, and acetic acid goes out very easily. So that's the easy separation. And then we have for the 2 separation, we have the pressure swing distillation. That's one alternative flow sheet already. Another alternative is to combine the membrane separation for water and put it into the distillation column for the reactor, and then we have another alternative. So like this, we can generate many alternatives. In fact, more than 10 we have generated. Which one is better? We will see afterwards. And now let us look at another way to do the same thing. Just 1 minute. We have to identify all the tasks from the reference. We identify all the phenomena building blocks, and then from that we will see how many phenomena building blocks we have. We have 15. We have 16,000 combinations, and from there we will take the ones we need. So example, here is a separation task. Here is a reaction separation task. And then we have the SPBs combination, which is a combination of PBBs. We have the reactor. Then we have some separation, and we have some 2-phase separation with reaction. And then from those SPBs, we can make a basic structure like a single-phase reactor or a multi-phase reactor. And then we take those multi-phase reactors and all those SPBs to generate whatever we want. So again, we come back to our reaction task and a separation task of 4 compound separation. We said that we will take the reaction task and then we put the separation task together to get rid of the water. And then on the top, we have 3 compound separation, which we combine with 3 compound separations, and we have different alternatives. And then we combine them together and we have the reactive distillation. So this is the way the phenomena have been combined. And then, as I said, we increase the number of reactive and non-reactive intermediate SPBs to get to the product specification we want. Okay, so you saw the example in 3 ways. Now here are some comparisons. We have the base case, then alternative 3, 4, 5, and reactive distillation. So you can see that reactive distillation is not necessarily the best. There is alternative 5, which is equally good as far as the reactive distillation is concerned. So many alternatives can be generated. And then we have the boundary, and within the boundary, all the solutions are within it. So it's a non-trade-off solution. So finally, opportunities and challenges and perspectives. Many opportunities exist, but targets need to be defined. For example, here, reaction is feasible, but downstream separation is difficult. For example, in the biopharma food industries, can we do them together in a single pot through intensification? That is a very good opportunity for many people who would like to apply PI. Then reaction is feasible, but reaction and separation tasks are energy intensive. Can we reduce the energy required? Or process is feasible, but is energy and or water intensive and generates waste. That's typical of chemical and petrochemical industries. Can we do something with PI? So which of these can we say that a priori a PI solution would be feasible? We can see, I'm just showing you these 2 that we have solved. We have solved many more of these kind of problems. And all of these processes can be converted into a reactive distillation or divided reactive distillation if the answer to all the questions on the right is yes. If the answer is yes, all we have to do is to find out what is the condenser duty, what is the reboiler duty, how many stages we need below the reactor, how many stages of reactive, how many non-reactive stages above the reactive. If we answer those 5 questions, we are able to convert any chemical process into a reactive distillation. And the phenomena blocks are already there. So if we look at the future, what we need to see is that we want to achieve sustainable development. We can have an integrated network of more efficient modules. We can have PI equipment, we can have smart materials, catalysts, membranes, and so on. And we can have this computer-aided process intensification methods and tools. All of these combined together will help us to get sustainable development. We can solve the reverse problem formulation and solution for PI alternatives, simultaneous material design and process intensification for hybrid operations with new materials, wider application of PI solutions, range of processes that can be improved, verification, and software. I think I already mentioned this in the previous lecture, so I will not go through it. It's the same idea that we need to integrate reality with virtual reality, and then the references. So with that, I will end my second lecture. If there are questions, I will take them now.
Okay. Yes. The first one is this phenomena-based design. If the phenomena consists of reaction and separation, will it always you in reactive distillation units? And which phenomena, for example, will it for the reactors? Yes.
So not necessarily. The example I showed for the methyl acetate, we have reactor followed by separation. So it doesn't have to be always reactive distillation. That depends on the criteria one has given, how much intensification one wants to do, which performance criteria one wants to take. Actually, one of our solutions is better than reactive distillation. So it is possible. The phenomena for membrane is actually, we have what are the phenomena involved for pervaporation. So we need permeation phenomena. So we have defined the tasks and the corresponding phenomena for pervaporation, molecular sieves, gas-gas separation, gas-liquid separation with membranes. So all of those are there. We say what is the phase contact, what is the phase separation scheme, technique. All of those will define which membrane and what type of membrane to use. So those phenomena building blocks need to be further developed. And again, anybody is welcome to collaborate with us to help us generate more alternatives. Next question.
How are the alternatives will be validated once generated by CAPI?
So there are different ways to validate. If we want to validate with a model, then we have to have a model available. So if people want to look at it from a unit operation point of view, that's why we convert our phenomena models into task and back into unit operation. But that unit operation can be a totally different kind of operation because different things have been mixed together. So that we can simulate. We can put in our models into the simulator and we can simulate that. But because it is totally new, nobody has got the actual unit operation. So it is, unless somebody actually builds it, it is very difficult to experimentally validate it. But through model, it can be done. And that's the challenge. Who will actually spend the money and build the equipment, a new equipment, and do the validation? That's why you see more reactive distillation and dividing wall column. And many companies I know have developed their intensified equipment, but it's confidential. So we do not know about it, but companies do have them. And if we can show that we can reduce maybe even 50% of the costs, companies may be interested. So we need here, in order to, and not keep it confidential. So if it is not made confidential, then other people will know it. If it is made confidential, nobody knows it. Another question?
Could you elaborate on the advantages and disadvantages of direct and sequential method?
Yes, the direct method will solve all the equations together, and then it is possible to solve the equations. Doesn't matter how big they are, what is the number of equations, if they are linear. So MILP for 2 million equations, 3 million equations can easily be solved. But MINLP for 2 million equations, it would be very difficult to solve. So that's where if you mean the sequential as the decomposed method, the decomposition method comes in, where we break down the big problem into sub-problems. We still satisfy all the constraints and all the equations, but we solve them in a sequence of sub-problems. And then many of those very complex problems can be solved. And the complexity always comes in because of the phenomena. Because if we have phase equilibria, or we have to calculate the permeance and diffusivity on all of that, those models are complex. Putting them into the set of equations would be very difficult to solve them. So if the problem is small, the nonlinear problem can be solved directly. If the problem is big, it is better to decompose the problem into sub-problems and then solve them. Any other questions?
There's no question now.
Okay, then the next lecture is also by me. It will be a short lecture, and after that there will be the software problem solution. Okay, so I will open the next one.